This video is for my Biology for Health Majors class. We're still in Unit 2. This is the third Unit 2 video on water's life-giving properties and water chemistry. So why is water chemistry so important to biology? Well, life's chemistry is tied to water. Life first evolved in the water. All living organisms require water, and cells consist of mostly water, about 75% water. But the universe is a big place. Would all life in the universe have a similar reliance upon water? There are other liquids. For example, take Titan. Titan is a moon of Saturn. It's quite cold there. It's pretty far away from the sun. It's so cold that water has settled down from a liquid into a solid, and methane, the gas, has settled down into a liquid. Titan has liquid methane oceans and islands made out of ice. There is plenty of liquid on Titan. It just isn't water. Could life evolve in such an ocean? Water is quite a unique liquid and a unique molecule. In this video, I'll talk about the unique chemical properties of water that make it responsible for life as we know it. Now, the tendency for two different kinds of molecules to stick together is called adhesion. Capillary action relies upon adhesion. That's how water moves against the force of gravity up a capillary or a narrow tube. And most plants depend upon adhesion to help transport water and nutrients from their roots to their leaves against the force of gravity. So here are some capillaries. They're just narrow tubes with different diameters. The narrower the tube, the higher the water will climb. The water's climbing because glass has an electromagnetic charge. It's polar, and water is as well. And remember, opposite charges attract, so opposite charges on the water and glass attract each other, which causes water to climb the tubes because the electromagnetic forces are pulling water against the glass upwards, like magnets. So the narrower the tube, the higher the water is going to climb. Because, water doesn't climb the air, it climbs the glass. And the narrower the tube, the more glass relative to air there is. Wood is filled with xylem, which are narrow capillaries that allow water to pass from roots to leaves. Capillary action is part of what helps water move upwards through a land plant. Now, plants that are submerged in water, they don't really have to worry about water transport, but on land, xylem are an essential adaptation for land plants who really have to fight the force of gravity to allow water to reach all of their tissues, all of their parts. You also see adhesion when water climbs into certain fabrics, like your towel when you're drying off. So the reason a towel dries you is because water is attracted to the fibers in the towel. So because of adhesion, the towel wicks the water away from your skin. Also, adhesion causes water to climb through paper. There's this experiment you can do where you put some ink on paper and you dip one end of the paper into water and just leave it for a little while, and the water will climb through the paper against the force of gravity because of adhesion. And it will pick up the ink as it climbs because the ink dissolves in water. So it picks up the ink as it climbs, and that causes the colors in the ink to separate because the different colors move at different rates through the paper. Larger molecules move more slowly through the paper matrix than smaller molecules. And so the different colors in the ink separate, and then you can see what colors each different ink is made out of. And the reason that works is because of adhesion. Now, cohesion is the tendency of molecules of the same kind to stick together. So adhesion was where water was sticking to something else, two different molecules sticking together. Cohesion is when the same kinds of molecules stick together. Cohesion is much stronger in water than in other liquids. Most plants also depend upon cohesion to help transport water and nutrients from their roots to their leaves. Now, you can watch water droplets falling on sand in slow motion, and if you do this, you'll notice that upon impact, a water droplet will begin to splash and spread out. The force of impact threatens to separate all those water molecules, but then the droplet recoils. It springs back to its original form, and it sits in a little sphere for a moment before it sinks into the sand. It will be pulled into the sand by adhesive forces, but for a moment before that happens, the cohesive forces cause the water to spring back to its original shape in a droplet and just sit as a sphere on the surface of the sand. Now, how well this works depends on the size of the sand particle and the force of impact, but it's pretty interesting to watch. You can search, I've put right here, let me get my little laser pointer. So right here, I've put the name of a pretty cool video that shows this. It's posted by APS Physics. It's another YouTube video where they just show these slow motion videos of water droplets hitting sand and what happens to them in slow motion. A fun way to spend part of the afternoon is watching water drops in slow motion in general, not just on sand. You can try the slow-mo guys, for example, but there are others. Watching water drops like rain fall in slow motion upon a still pond, you can see how they bounce a couple of times before they merge with the body of water beneath them. So water's cohesive properties cause water droplets to hold together, even against the force of impact. Cohesion causes water drops to beat up on your freshly waxed skis or on your freshly waxed car, instead of spreading out flat. Each water molecule is a little magnet that attracts the other water molecules around it so that they all stay together. So plants transpire water from their leaves. It happens when they open up pores in their leaves to breathe. Just like you lose water when you breathe in your humid breath, plants also lose water when they breathe. They have these pores in their leaves that open up to allow carbon dioxide in and oxygen out. But water evaporates from the leaves as well. And the water that evaporates from the leaves are cohesive with the water molecules just below them in the capillaries, in the xylem. And that pulls the water molecule beneath them upwards as they evaporate. And once that water molecule moves upward, it drags with it the water molecule below it, and the water molecule below it, and the water molecule below it. Each water molecule is attached via cohesion to the water molecule below it in the capillary. So when water evaporates from the leaves of a tall tree, they pull a long line of water molecules upwards, like a train of cohesive water molecules that extends from the leaves to the roots. Cohesion and adhesion together allow water to travel from soil up to the tops of trees as tall as redwoods against the force of gravity, without even a pump like a heart to help the water move. The water molecules are more attracted to each other than they are to the air above them, and so cohesion causes the molecules at the surface of the water to form a sort of barrier that prevents entry for light objects, especially if those objects have a lot of surface area to distribute their weight. So hydrogen bonds give water high surface tension, making the surface of the water behave like it's coated with an invisible film. Lily pads and insects can sit on top of water without falling in due to surface tension. Surface tension doesn't play so many obvious roles in your life because you're too big to notice it very often. Though it does affect your physiology internally, like inflation of your lungs is affected by surface tension. But surface tension does affect the small world very much. Together, cohesion and surface tension allow water to persist in droplets, which makes water available for all kinds of creatures to drink. This ant can even carry a drop of water without a vessel to put it in. It just plops the droplet of water on its head and it all stays together because of the surface tension of the droplet. The barrier between the inside of the droplet and the outside of the droplet is difficult to break because of those hydrogen bonds forming that sort of like a film almost around the surface of the droplet. In their world, in the ant's world, in the small world, water has different characteristics than it has for you. Water actually has the same characteristics, it's just that some of those characteristics are more obvious and more meaningful at these smaller scales. For example, if somehow an insect did break through the surface tension, like, for example, if a raindrop fell directly on the animal and the surface tension was broken by the impact of the fall, the insect could become trapped within the drop and not be able to escape. This ant finds itself unable to escape the water droplet. It doesn't have the strength to break through the cohesive forces of surface tension. It will drown. And at the other end of the spectrum are diving bell spiders. These aquatic spiders bring air bubbles down with them. So they have this fuzzy, like velvety abdomen, and that velvety hair on their abdomen traps air. Because of the boundary created by surface tension, the water stays distant, leaving them surrounded with a little oxygen bubble. They bring these oxygen bubbles down to their nest, one after another, adding more and more until they can just sit there in their air bubble waiting for prey to fall into their aquatic webs. So you can see here, this spider, it has this air bubble around its abdomen, and they breathe through their abdomen. They have these little pores on their abdomen, these vents that allow them to breathe. So they have this, it keeps this air bubble around its abdomen, and this spider can go to this, there's this larger air bubble, so it'll keep bringing small bits of air and add it to the larger air bubble, and then they can hang out in there. And these diving bell spiders live their entire lives underwater. They mate underwater, they hunt underwater, that's where they build their webs, they eat underwater, but they breathe air. It's just that because of surface tension, they can bring the air down with them. Microbes might live their entire lives inside a water droplet. In fact, water droplets are how many pathogens move from person to person. COVID, for example, moves in water droplets. Some microbes complete their life cycle up in the clouds and then come down with the rain. They're living inside little water droplets that make the clouds. The conditions of the water drop is their whole world. They reproduce, live out their lives, protected by the walls created by surface tension. Now this is just my laser pointer right here. And you can make a microscope out of a laser pointer and a bead of water. The bead of water, because it maintains its circular shape, acts as a lens that magnifies images, it magnifies light. So the way you build this, you just get a regular old laser pointer. This is just one that I use in classrooms. And you get a paper clip. And you extend out one arm of the paper clip. And right down here, you can see I've created a little loop at the end. And when I turn on and then I've attached it with a rubber band. Now, when I turn on the light for the laser pointer, the light will shine through the center of that loop. Now you can dip that loop into water and draw up a little bead, and it keeps its shape because of cohesive forces and surface tension. Now you can turn off the lights, turn on the laser pointer, and project it onto just a flat surface, a white flat surface, and you can see if there's any microbial life in that droplet. So to make this video, my daughter and I gathered some pond water from the duck pond at University of New Mexico, and we kept it in a little jar and let the microbes proliferate for about a week. And this is what we saw, shining the light through it. You can see all these single-celled organisms. It's in one single drop of water. There's an entire city of microbial life. Water also has a high specific heat capacity, which means it can store a lot of heat without changing temperature. So temperature is a measure of the speed of molecules in a substance. So when you're measuring the temperature of something, you're measuring molecular speed. So when you touch something that has a very high temperature and you burn your finger, what's happening is those molecules in the thing that you touched, they're moving, vibrating so quickly, and they slammed at high speed into your finger and damaged the tissue because of their speed. So temperature is a measure of how fast molecules are moving. And when you add heat energy to something, you cause those molecules to vibrate really quickly. So a lot of heat energy must be added before the molecules in water will actually speed up. At first, as you got a pot of water on the stove, and at first you're adding heat energy from the stove. You turn the stove on. At first, all that energy is going to breaking hydrogen bonds between water molecules. But those hydrogen bonds just keep forming. They break, they reform, they break and reform. And so it takes a while to get to the point where the molecules will actually start moving much faster. There has to be a lot of energy invested before there's an actual temperature change. Hydrogen bonds make it difficult to change the speed of water molecules, and that makes it difficult to change the temperature of water. And so water moderates the planet's temperature. So if you've ever lived by a large body of water like a lake or the ocean, you'll know it takes water much longer to change temperature than the air. In the fall, the water is warmer than the air because the air is cooling down and the body of water is taking longer to lose the heat that it collected during the summer. In the spring, it's the reverse. The water is colder than the air in the spring because the air is heating up faster than the water is heating up. And also, if you've ever lived by a large body of water, you know that the water temperature doesn't fluctuate from night to day as much as the air temperature does. It stays fairly constant throughout the day and night. The high specific heat capacity of water is also why humid places don't have as much of a temperature swing between the day and night as dry places do. Here, where I live in the desert, you could have like a 20-degree difference between night and day. That doesn't happen where I grew up in humid Pennsylvania, right? So water moderates the planet's temperature. We also use it to regulate our body temperature, not just because the water inside of us prevents our temperature from changing very much because it can absorb a lot of energy without changing temperature, but also because when water leaves the surface, a lot of heat is lost with it. And so this is responsible for evaporative cooling. In the desert, we have swamp coolers, and you put a swamp cooler full of water on the top of your house because heat rises, and it absorbs all of the heat from your house. And then that water is pumped through these membranes and then there's a fan, and it allows all the heat to, all the water to evaporate, and it takes the heat from the house with it as it evaporates. So the heat energy, the water in the swamp cooler absorbs the heat energy from the house, it evaporates and takes that heat away. And that's also how sweating works. So swamp coolers and sweating, sort of the same thing. The way evaporative cooling works is you put a bunch of heat in water, and then you let the water evaporate, and it takes the heat energy with it. Now, water can exist as a gas, a liquid, or a solid. But water is less dense as a solid than as a liquid because of the hydrogen bonds, again. Now, water is the only substance that is denser in its warmer liquid form than in its colder solid form. Typically, things become more dense as they get colder because the molecules are more still when they're colder. Remember that temperature is a measure of molecular movement. So as the heat energy is removed, as the thing cools down, the molecules slow down and they settle. And as they settle, they squish together. So usually the colder a substance is, the more dense it is. Water does get denser as it gets colder up to a point. And that point is the freezing point. So water gets denser as it gets colder until it freezes, and then it expands. Things that are less dense float on top of things that are more dense, so this means that ice floats on water. So when water freezes, each molecule forms a stable hydrogen bond with its neighbors. And there's a crystal geometry that arises. And this geometric pattern forces the water molecules to spread out because of the geometry of their hydrogen bonds. And that is what makes ice less dense than water. Because ice is less dense than water, it floats, which is very unusual. Usually this cooler solid form sinks on top of the warmer liquid form. So here you can see liquid water is down here, and you can see when they're tumbling all around each other, they're actually able to squish together a little bit closer because these hydrogen bonds keep breaking and allowing the molecules to get closer together. But these hydrogen bonds, if you remove the heat energy and the molecules become still, these hydrogen bonds become more stable. And they form and they're kept. And that's what ice is. So ice has this crystal structure, these repeating patterns within it. And so that geometry is more spread out. That causes the ice to expand. If ice on the surface sank, and then you have a layer of ice down at the bottom of the ocean, and then you make more ice at the top, then more ice would form at the top and then sink, and then more ice would form at the top and then sink, and then more ice would form at the top and then sink. So you would it would cause the oceans to turn to ice from the bottom up, and the whole ocean would freeze solid. But because ice floats, it behaves as insulation, like a blanket on the water that lies beneath it. So even in the coldest parts of the globe, bodies of water are never frozen solid beneath the surface. And this allows life to persist in the ocean even during extreme ice ages. Water is a universal solvent. Now, for a chemical reaction to occur, two molecules must come in contact with each other. If they are sitting on a solid surface, it's not likely that they're going to come in contact, right? So if you have sodium over here and chlorine over here and they never meet each other, are they going to exchange electrons? No, not likely. They have to actually come in contact with each other to have an electron exchange. But if they're floating in a solution, then they're moving around, that increases the likelihood that they'll bump into each other, they'll collide, and a chemical reaction between them can occur. So for a chemical reaction to occur, two molecules must come in contact with each other. Solvents, therefore, increase the rate of chemical reactions. So a solution is a liquid consisting of a uniform mixture of two or more substances. You have the solvent, and that's the dissolving agent. You have the substance that's dissolved, and that's the solute, and then and an aqueous solution is one in which water is the solvent. So salt water, that's a solution. Salt water is a solution. The solvent is water, and the salt is the solute. Now, water is a universal solvent because of its polarity. It has positive and negative charges, and most other molecules also have some sort of electromagnetic charge. They're either ionic or polar themselves, which means that water is attracted to almost all molecules, which means almost everything will dissolve in water. And that really allows the chemical reactions that are conducive to life to occur. Because life is, to stay alive, there's, oh gosh, who knows how many chemical reactions happening in your cells all the time, all day long, every day. So that can only happen because all of those molecules are dissolved in water. They're floating around, they're colliding, it's dynamic. If you were all dried up, right, that wouldn't be able to happen. Just to reiterate water's life-supporting properties, we had adhesion, we had cohesion, we had surface tension, we had water's high specific heat capacity, which regulates the temperature of a body or the planet. Solid form of water, or ice, is less dense than the liquid form of water, keeping our oceans always liquid. And its role as a universal solvent. Now, methane oceans won't have any of these properties because methane, remember from the last video, is nonpolar. It's carbon surrounded by 4 hydrogens, and carbon and hydrogen form nonpolar covalent bonds. All the electrons are equally spread out across the molecule. There's no accumulation of positive or negative charges anywhere, which means methane has no attractive electromagnetic charge to anything. So fewer things are going to dissolve in methane. Things will either float to the top or sink to the bottom, and not very much is going to be dissolved in the methane ocean. And you're not going to have adhesion, cohesion, surface tension, high specific heat capacity. It's not going to regulate the planet's temperature the way water does. And the solid form is going to be more dense than the liquid form. So all of these things would mean that, that doesn't mean that no life could evolve in a methane liquid ocean, but it's really questionable whether it could. If it did, it would look something entirely different than life as we know it. So I have a couple last notes about the chemistry of water. In water, a small percentage of water molecules break apart into ions, and these ions create acidity or alkalinity. So water is H2O, right? So water is H2O, and that kind of looks like that, right? That looks like that's what that molecule looks like. So water can split, and so if this covalent bond is broken, the electrons go with the oxygen typically, which leaves a proton by itself, which we call H+, and then it leaves the OH with extra electrons, so OH-. So in liquid water, you're always going to find some hydronium ions and some hydroxyl ions. Hydronium ions, the more of those you have, the more acidic the solution is. Hydroxyl ions, the more of those you have, the more alkaline the solution is, or the more basic the solution is. Both these ions are very reactive. Right, so here's a pH scale pH is a measure of acidity, and it exists on a scale of 0 to 14. And these are some common household items of various pHs. And you'll notice that bleach and oven cleaner, which we know is really caustic, it's not very good to get on your skin, that's not acidic, it's basic. Bases are reactive, just like acids are reactive, but for different reasons. They have a slightly different chemistry. Now, battery acid, lemon juice, that's more acidic. So pH is a measure of acidity, and more specifically, it's a measure of hydronium ions. So the more acidic something is, the more hydronium ions it has. And the less acidic something is, fewer hydronium ions. Now, things with few hydronium ions tend to have a lot of hydroxyl ions. pH is not a measure of hydroxyl ions. It's specifically a measure of hydronium, but there is an inverse relationship between hydroxyl ions and hydronium ions. So the more hydronium ions you have, the fewer hydroxyl ions you have. The more hydroxyl ions you have, the fewer hydronium ions you have. Okay, so bases have a lot of hydroxyl ions, and acids have a lot of hydronium ions. So the pH scale is a little counterintuitive, right? Because the more hydronium ions something has, the more acidic it is, but the lower the pH. So you could just remember that it's counterintuitive and say a low pH means high acidity, high hydronium ions. Or you could learn the math. And some people, it only makes sense if they see the math. Some people don't want to see the math, but I'll show it for those of you who'd like to see it. Okay, so let's start by looking at the very acidic pH of 1. So pH 1. What does that mean? It refers to the number of hydronium ions in the solution. So pH of 1 means that there are 10 to the negative 1 moles of H plus per liter. And what is a mole? It's just a unit to measure the number of atoms. It's a number of atoms. So it's a number of hydronium ions. So it's 10 to the negative 1 moles of hydronium ions per liter. Okay, so the 1 in the pH comes from an absolute value of this exponent. And so what does that equal? Well, that's 0.1 moles of hydronium ions per liter. All right, so how about a pH 7? And this is a neutral pH, but it's less acidic, which means it should have less hydronium ions, because more acidic things have more hydronium ions and less acidic things have less hydronium ions. So pH of 7 is less acidic, it should have less hydronium ions. So let's look at that 7. That's 10 to the negative 7th moles of hydronium ions per liter. And what does that equal? What is that number? That's 0.00. I think we need 6 zeros and a 1. 1, 2, 3, 4, 5, 6, 1. Okay, moles of hydronium ions per liter. All right, so which of these numbers is bigger? Right, the bigger number is this. This is a bigger number than this other number. So pH of 1 has more hydronium ions than a pH of 7. And so if you were going to talk about like a pH of 14, oh my gosh, that's crazy. So 10 to the negative 14, there's so few hydronium ions. Now, usually substances that have few hydronium ions have more hydroxyl ions. 10 to the negative 14th moles of hydronium per liter for the most, this is as basic, as alkaline as it gets. So we need 13 of these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and a 1 moles of hydronium ions per liter. So that's very, very few hydronium ions. Hydronium ions are very reactive. That's what makes acids caustic. So hydronium ions, it's a little positive charge floating around with no electrons to neutralize it. So it bumps into things and it wreaks havoc on other molecules, like the molecules that build your cells, pulling them apart and destroying your cells, right? That's why acids are destructive to tissue and to other things. On the other hand, hydroxyl ions, so this is a hydronium ion, this is a hydroxyl ion. Hydroxyl ions are also very reactive. They create all kinds of free radicals. It's a little like a little negative charge floating around, and it tends to give its electrons to things. It throws its electrons at things. And so that tends to break up molecules in the cell as well, which is why, people always think bleach is acidic because it's caustic. It's actually alkaline, but things that are alkaline can be quite dangerous as well because, they don't have the exact same chemistry, but they're still quite reactive. They still disrupt molecules that are holding the cell together. So a water molecule, when it splits apart, that leaves a hydrogen alone with no electrons, and it gives the hydroxyl group extra electrons. And that just happens naturally in water. Adding different substances can push a material to an acid by releasing hydronium ions, or towards a base by creating more hydroxyl ions in the solution. And that is the chemistry of water.